Most people look at a QR code and see random little squares. But it is not random at all. In fact, a QR code is carefully designed so your phone can find it, line it up, measure it, and read it in seconds. And the biggest clue is right in front of you, those 3 large squares in the corners. Those are not decorations. They are landmarks. Once you understand those landmarks, the rest of the QR code starts to make sense. You can see why it scans so fast, why it works from different angles, and why it can still scan even when part of it is scratched, dirty, or covered. So in this video, let's break it down in simple terms. The finder patterns, the timing lines, the alignment patterns, and the error correction system that makes QR codes much smarter than they look. QR codes are not random squares. The first myth to clear up is this. A QR code is not just a random block of black and white boxes. It may look chaotic, but every part has a job. Some parts help your camera locate the code. Some parts help it understand the size of the grid. Some parts help correct damage. And the rest carries the actual data. So what looks messy is really a well-organized map made for machines to read very quickly. The 3 big squares are landmarks. Let's start with the easiest part to spot. The 3 large squares in the corners. These are often called finder patterns or position detection patterns. Their job is to tell the scanner, here is the code. Here is its shape. And here is its direction. That is why a QR code can be read from any angle. Your phone does not have to guess where the code starts. Those 3 corner squares give it strong reference points right away. Think of them like landmarks on a map. Before your phone reads the message, it first finds the landmarks. Why are there 3 instead of 4? A lot of people wonder why there are 3 big squares instead of 4. The simple answer is that 3 are enough to define the position and orientation of the code. With those 3 corners, the scanner can figure out where the code is, how it is rotated, and how to begin reading the rest of the grid. That design helps QR codes scan quickly while keeping more space free for actual data. So those 3 squares are doing a lot more work than most people realize. The timing lines help the scanner count. After the scanner finds the code, it still needs to understand the grid. That is where the timing patterns come in. These are the alternating black and white lines that run horizontally and vertically between the large finder patterns. You can think of them like a ruler or measuring tape built into the code. They help the scanner figure out the size of the tiny squares, keep the rows and columns lined up, and stay on track even if the image is a little blurry or angled. Without those timing lines, the scanner would have a much harder time knowing exactly where one tiny square ends and the next one begins. The alignment pattern helps with distortion on many QR codes, especially larger ones. You will also see a smaller square inside the code. That is the alignment pattern. Its job is to help when the code is slightly warped, curved, or viewed from an awkward angle. Denso Wave says alignment patterns help the code read smoothly even when the image is distorted, and Industrial Guidance describes them as extra reference points inside the grid. So if a QR code is printed on packaging, a bottle, or another surface that is not perfectly flat, the alignment pattern helps the scanner correct for that distortion. The white border matters too. There is another part people often ignore: the empty white border around the code. This is called the quiet zone. It looks like blank space, but it matters a lot. The quiet zone helps the scanner separate the QR code from the background. Without that clear margin, the camera may have trouble telling where the code ends and the surrounding design begins. Official guidance from Denso Wave says a standard QR code needs a quiet zone that is 4 modules wide on all sides. So even the blank area is part of the design. where the actual data is stored once the scanner has used the finder patterns, timing patterns, alignment patterns, and quiet zone to understand the code, it can focus on the remaining small squares. That area holds the actual information, along with extra information that helps decoding. Depending on the QR code, that data might open a website, show a ticket, connect to Wi-Fi, store contact details, or trigger a payment page. The important thing is this: the visible pattern is really a machine-readable layout, not random art. Every section is placed so the scanner can move from locating the code to decoding the message. Why damaged QR codes still work now? For the part that surprises most people, a QR code can still work even when part of it is damaged. That is because QR codes include error correction. In simple terms, they carry backup information along with the main data. Denso Wave explains that QR codes use Reed-Solomon error correction, which helps restore the original data when part of the code is dirty or damaged. That means the scanner does not always need a perfect image. If enough of the code is still readable, it can rebuild what is missing and still give you the right result. That is why a scratched QR label or a slightly damaged ticket can still scan. Error correction is a trade-off. There is a trade-off, though. More error correction usually means more reliability, but it also takes up more space. QR codes have 4 error correction levels: L, M, Q, and H. Denso Wave says level M is commonly used, and higher levels like Q or H are more useful when codes may get dirty or damaged. So a QR code is not just storing the main message. It is also deciding how much backup information to include. That is one reason 2 QR codes can look different even if they are doing similar jobs. Size changes with the amount of data. QR codes also come in different sizes, called versions. Denso Wave says standard QR codes range from version 1, which is 21 by 21 modules, to version 40, which is 177 by 177 modules. As the amount of data goes up, the code usually needs more modules, so it becomes denser or larger. That is why some QR codes look small and simple, while others look much more crowded. More information and more error correction usually mean more squares. A quick history of why QR codes were designed this way. QR codes were released by Denso Wave in 1994, and the name QR stands for Quick Response. The goal was fast reading and more data capacity than older barcodes. Denso Wave also says the code could be read more than 10 times faster than other codes at the time, and later made the specifications publicly available, which helped the format spread widely. So the reason QR codes look the way they do is not style. It is speed, accuracy, and reliability. The design had to work in the real world, not just on paper. One quick safety note: QR codes themselves are just tools, but the link behind them can still be risky. The FTC warns that scammers sometimes hide harmful links in QR codes or place fake QR stickers over real ones, so it is smart to scan codes only from sources you trust. So the next time you see a QR code, you are not looking at random squares. You are looking at a carefully planned system. The 3 large corner squares act like landmarks. The timing lines act like a ruler. The alignment pattern helps fix distortion. The quiet zone gives the code room to be seen clearly. An error correction gives it enough backup information to survive dirt and damage. That is why QR codes are so useful. They are compact, fast, flexible, and surprisingly resilient. Once you know what each part does, that little black and white box stops looking random and starts looking brilliant. If you enjoyed this video, please like, share and subscribe. Then tap the bell icon to turn on all notifications so you never miss any of our future videos.